In this presentation, I'll be discussing Lab 4, which looks at oscillations. The purpose of this lab is to explore the physics behind a mass oscillating vertically on a spring. The observed data we glean from Tracker will be compared to model data using GlowScript. We will compare the x and y position of the mass over time for observed and the model. The x and y positions of the mass over time of the observed data and the model data followed each other closely. The changes in kinetic energy, gravitational potential energy, spring potential energy, and the total energy were also plotted using the model. The physical principles we used included an F-net equation, which equals F grav plus F spring. F grav is 0, negative mg 0, and F spring is 0, ks 0. We also used Newton's second law. We used the position update and velocity update formulas, which are listed here. And we also used the energy principle, delta E equals W, where W equals 0 in this case. So delta E, or 0, equals the delta K of the mass plus delta U of gravity plus delta U of the spring. And this ended up equaling 1/2 mv final squared minus v initial squared plus mg delta y plus 1/2 k s final squared minus s initial squared. We needed to use the net force equation in order to calculate F net to be used in the position and velocity update formulas. These two formulas were used to update the position and velocity of the mass in order to get our model position data. Finally, we used the energy principle to track the changes in energy our model predicted over time. Here is our Tracker video. In this case, the system was the mass, the spring, and the earth, and the surroundings were nothing. Tracker was used to track the position of the mass over time increments of t equals 0.095 seconds, giving us the data in the table on the bottom right. Our initial conditions for our code: the mass was 0.402 kilograms, the spring stiffness 6.83 newtons per meter, the relaxed length L naught 0.123 meters, and the initial stretch length L 0.7 meters. The initial position was negative 0.119, negative 0.637 meters. The initial velocity was 0 and delta t equals 1/210 seconds. The code worked by calculating both the gravitational force and the spring force and adding them to get F net for each time interval. The mass's position and velocity was then updated using the position and velocity update formulas. The spring was updated by finding S, L minus L naught, for each time interval. Finally, the following energies at each time interval were found: kinetic, gravitational potential, spring potential, and total. The change in energy was found by subtracting the previous energy calculated from the current energy calculated. A CSV file of our observed results were inserted into the code to be compared with the position data from the model. Here's the output of our code. It output 3 plots. The first depicts all the energy changes found by the model over time. The second depicts the x position over time for the computational model in blue and the observed data in red. The third plot depicts the y position over time for the computational model and the observed data. For our position versus time graphs, the model followed the observed data very closely. In x, the model seemed to be shifted a bit to the right, and in y, the model's amplitude is a bit higher. Some potential errors could be that the model neglects the mass of the spring. There could also be other possible forces acting on the system, such as the drag force from the air, and there could also be human error in Tracker. For the energy graph, we know it's a bound system, so the total change in energy should be 0, and we see that delta E is 0 in the graph, so that follows through. Delta U grav and delta U spring are close inverses to each other, and delta K balances out any differences in the delta U's, so the total energy sums to 0. Is the energy principle satisfied? The energy principle states that energy is neither created nor destroyed, and delta E equals 0 in the bound system. In this case, delta E equals delta K plus delta U grav plus delta U spring. The graph shows that delta E equals 0, so therefore all the energy sum to 0. So therefore the energy principle is satisfied. For the estimates of oscillation periods, x was estimated to be 1.91 seconds, while y was estimated to be 1.66 seconds. The period of oscillation for y is less than that of x, so one oscillation will occur faster in the y direction. This means that over time, the graphs of x and y position over time would diverge, even though they may look similar at first over a shorter timescale.